Welcome back. Let's do these four things right here, all right? Let's take bubble sort, insert sort, and selection sort and talk about which is best, right? Now you may have a favorite, but in terms of time complexity, which is our kind of standard way of evaluating the efficiency of algorithms, we want to know which one's best. So we'll use our rules of thumb for determining the time complexity of these three here and see which one's better, if any. Then we'll look at optimization, right? There's a classical optimization for bubble sort, and we'll see, does that matter? And then let's do some empirical testing of bubble sorting. That is, we'll measure it. And then I've got a mathematical analysis of bubble sort, all right? Because we have three ways of doing analysis. We've got empirical testing, we've got mathematical analysis, and we've got rules of thumb. So we'll do sort of all three of those with bubble sort, and we'll also do the rules of thumb with insertion sort and selection sort. All right, that's what we're going to do. Okay, I've got the source code for homework 0, which you should all be familiar with by now. Let's use our rules of thumb type analysis for these things. Okay, so for bubble sort right here, let's get in there. This is bubble sort. That's the guts of it right there. You've got a constant time swap. That's big O of 1. You've got a constant time comparison on the if. Let's just assume that this if always executes. And so this whole block is constant time. Okay? It's in a loop that executes a certain amount of time. How much? Well, we can tell right away. It looks like it's going from n to 0 because the counter's going j times. So this loop right here is n. It's going n times. N is size in this example, right? So this loop is going n times or size times. And its target is constant. So the whole thing I have highlighted right there is n, exactly n. Okay, the outside is going from 0 to n. So this outside is exactly n. Okay, so we've got this chunk right here that's n inside of a thing here that's n. So the whole thing together is n squared, all right? This whole thing together is n, where's the caret on this? N squared, all right? What about insert sort? That's this guy, insert. This is insert sort, right? What about it? Well, we've got an outer loop that's going n times. We've got some constant time statements that we can ignore. We've got a constant time statement we can ignore. Okay, we've got a constant time target of an inner loop. This loop is going from, let's see, where's the decrementer? J is going down. So J starts at I. And the first time through I is 0, so the first time through on the outer loop I is 0. So this J is starting at 0 and going to 0. And there's also this thing here which may terminate the loop. So we got to figure the worst case. The worst case is it goes to 0. Okay. I mean, it may get to a case where this comparison fails, which would terminate the loop earlier, but we use worst case, right? So worst case is this guy goes all the way to 0. So I is 0, that means J goes from 0 to 0 the first time, but then as I grows, so I will become 1, and then this loop will go from 1 to 0, then I will become 2, and this guy will go from 2 to 0. So as I gets bigger, this loop here starts approaching n. So it's less than n. And each time it executes, it starts getting closer to n. So we'll figure worst case and just call it n. Okay, so worst case, we've got some n stuff with a lot of a lot of assumptions and worst case scenario type assumptions, but let's call it n. And that n thing is inside of this n thing. So the whole thing together is roughly n squared. It's not exactly n squared, it's less than that, but we're rounding, you know, we're doing worst case stuff to figure n. So, you know, worse to a close, a rough approximation, bubble sort and insertion sort are both n squared algorithms. Okay, what about selection sort? Let's do our rules of thumb analysis on this. So we've got an outer loop, I, that goes from, okay, so n is size. So it's not exactly size, it's size minus 1. But for large n, that 1 doesn't make any difference, right? If size were a million, you know, a million minus 1 is still pretty much a million. So that's the kind of rough kind of, you know, what we call rules of thumb kind of judgments that we have to make. Okay, so let's just say I goes from n to, it's going down by 1 there, the decrementer, to 0. Okay, so it's going, I is going from n to 0, so it's going n times. So the outer loop, the outer I loop is going n times. What about the inner loop? So let's see, j is set to 0 and j is going to I. So it's like the one we just did before, right? For the first time through on the outer loop, I is n, so j will go to from 0 to n. This guy will decrement, the outer loop will decrement, and this guy will go to a little bit less than n, or 1 less than n. And then I will get smaller, and this will go from 0 to, you know, smaller and smaller and smaller. Each time this j loop executes, it's going less times. So what do we do with that? Well, we take the worst case and we just call it n. We say that the j loop is always executing n times. That's the worst case. The stuff inside is all constant time, so we can ignore that constant time stuff. Once again, this stuff down here is, the swap is constant. We can ignore that too, and these initializations are constant. Those are just declarations, but anyway, constant. Okay, so we're calling the inside n, roughly speaking, we're rounding it to n, and the outside is exactly n, so we've got n times n. The whole thing is n squared. So to a rough approximation, these three algorithms have the same complexity. Bubble sort is exactly n squared, whereas insertion sort and selection sort, they're slightly less than n squared, but for large n, it's not going to matter. So we take the worst case on things and we expand them to the worst case, and we use that. And I'm saying that it doesn't matter for large n, that these kinds of rough case approximations don't matter. Let's look at that a little more detail. All right, let's look at bubble sort in more detail. So what I have here is an unoptimized bubble sort. That is, the inner loop goes exactly n times, and the outer loop goes exactly n times. So the whole thing together is n squared exactly. No rough worst case approximation. It's exactly n squared. But we could make it like the other two algorithms by making a simple change here. And I don't want to mess it up, but what is the change? So if you make, well, let's just get into the, here, I've got it pulled up. Here's the optimized and the unoptimized version. So here's the unoptimized version highlighted right here. This Excel file is posted for you guys. You can pull it up and look at it. But the unoptimized version is exactly n squared. The inner loop is going from size to 0, and the outer loop is going from 0 to size. So the outer loop's going n times, the inner loop's going n times. Don't worry about the -1. It makes really no difference. So this is exactly n squared. But if I change and make this a small change and make the, where is it? Here, in the conditional. Instead of j going to 0, j only needs to go to I. So as the I is increasing on the outer loop, the inner loop is going a little bit less each time. Okay? What does that look like? I have an optimization. I have this exe file here that I've posted in the demos section of the website. And if you run that, this is an optimized BubbleSort. Let's go ahead and run that. So we're floating up to 1 now. So the inner loop's going to go all the way to the top the first time. Okay? So 1's at the top. There's no reason to look at it again. So the 2's getting floated up. The 2 is done. There's no reason to look at it again. Right? So the inner loop, which is doing these comparisons, can go 1 less each time. That is, it doesn't have to go to 0. It can go to I. Okay? So this is the optimized version of the BubbleSort. Now it's going to be a little bit faster than the unoptimized version. But does it matter? Remember, we're only interested in large n. For this is, so n is what? On this thing it looks like 20 numbers. It's going to be plenty fast. But we're concerned about millions of numbers. And does it matter for that? Well, it turns out it really doesn't in terms of time complexity. Let's look how the large ones dominate. And most of the algorithms spent kind of up on the large part of the array. Okay, let's look at the rest of this Excel sheet. So what I did over here in Excel is I did an empirical analysis, right? As well as the rules of thumb. The rules of thumb is what we did earlier, just with the looking at loops inside of loops and applying those rules. Okay, but over here, I actually put a counter in there, right? I actually somewhere in here, I think I did counter plus plus on both of these guys, and I generated these two sets of numbers. So you look for small n. They're, well, here real small n. There's a big difference, right? Like here, this is the unoptimized algorithm takes 9 cycles. The optimized algorithm takes 6 cycles. That's like 2/3, you know. So it's like 1/3 faster, right? But what about large n? Down in here, the optimized algorithm takes 1640 and the unoptimized algorithm takes 1681. That's only, what's the percent difference on that? It's 40 out of, it's not much, a couple of percent. And that's for a problem size of 41. If you had a problem size that really matters, you know, like that big, the difference between these two numbers would be super tiny. Okay, super tiny. So there's a couple of lessons here. One is that these kinds of optimizations, which you may have been taught in your beginning programming class, they really don't matter. For what matters is the time complexity of the algorithm. It makes far more difference because for small problems, they're going to execute quickly. It doesn't matter. But for large problems, these kinds of small optimizations that you might have made, they don't make any difference. Okay, so back to this this code over here. We've got 3 algorithms: BubbleSort, insertion sort, and selection sort. Now, you may have a preference for one of these or versus the other. One of them may look faster to a human. You may just like the way the code looks. Maybe you like BubbleSort. I like it. It seems pretty simple, but maybe you like insertion sort. The point is, in terms of time complexity, they're all the same, even with optimizations. Even though iSort has a little bit of an optimization, selection sort has a little bit of an optimization, and BubbleSort doesn't, although you could put that very same kind of optimization in BubbleSort. It doesn't matter. For large N, for big problems, all three of these guys are N squared. Okay, that's an important concept, because if you hadn't had a data structures class, maybe you would think that one of these was better than the other, when it makes no difference whatsoever. You shouldn't be spending your time at your job, optimizing something when it makes no difference. Okay, so that's the point. So back to our methodology. We have three methods for solving or for analyzing algorithms. We can do the rules of thumb. That is, we can kind of look at these loops and whatnot. We can do that. We can do an empirical analysis. That was, we can put a counter in there and count the thing and generate some numbers and look at the graph. We can do that. The third thing we can do is a math analysis. Okay, so let's look at that. Okay, so what I've got here is a mathematical analysis of BubbleSort I'd like to show you. So we've already, for the unoptimized, it's N squared. It's just the inner loop goes N times, the outer loop goes N times, it's done. But what about the optimized version? Okay, for the optimized version, what happens? The first time the loop executes, it goes all the way to the top of the BubbleSort, right? It goes N times. The second time the inner loop executes, it goes one less, so it goes N minus 1. The third time it goes N minus 2, like that, all the way down to 0, or N minus N. That's what it does. This is exactly how many times, mathematically, that the optimized version of BubbleSort executes. So now we can just do some algebra. So we can, these are all pluses in here, there's no multiplications, they're all pluses. So you can pull the n's off to one side, and then you can pull all the numbers off to the other side. And all these n's add up to n squared. And all these numbers, does this look familiar? These numbers are the arithmetic series that we looked at in the math notes. This is just 1 plus 2 plus 3 plus 4 all the way to n with a minus sign in front. So we happen to have a formula for that of n plus 1 over 2. This is the formula for an arithmetic series. So throw that in there and you get n squared minus n times n minus plus 1 over 2. You get that. So this is the time complexity of optimized BubbleSort exactly. Now what is that? You can kind of do some algebra to make it look a little different, but in the end, it's, you can use whichever one of these formulas looks or has more meaning to you. But I generated some numbers, and for small n there's a bit of a difference. But if you put some very large n's in here, which I should do, but if you put in like super big, you'll see that these two numbers are going to be close together, similar. So I'm just reiterating the point that the optimization doesn't matter much. There's that. The second point I want to emphasize is that this is just a BubbleSort, and this math, we got lucky. We happen to have this formula for a arithmetic series, and we happen to be able to apply it. Most of the time, for most of the code you're going to write in real life, it's a mess. There's loops, and there's loops inside of loops, and loops plus loops, and all kinds of stuff. Being able to do math on that is very unlikely. Okay, so you're left with, of our three analysis techniques, that is empirical analysis, rules of thumb, and math, you're mostly left with, honestly, the empirical analysis is the most practical one to use. Just put counters or timers in your code and get the shape of the curve, and then extrapolate what that would look like for big N. And rules of thumb a little bit will help you when you're writing code and when you're analyzing code, but math, not so much. Now, someday, maybe somebody will figure out a way to analyze code, and then by then the computers will be writing code themselves, and we'll all have to get different jobs. But anyway, I think that's it, right? Did I cover everything? Yeah, bubble sort, insertion sort, select sort, they're all the same in terms of time complexity, although one may look better than another to you personally. Is optimization worth it? Might not be. Most of the time it isn't. Time complexity matters way more than small optimizations. Time complexity is the most important thing. You can do empirical testing because the math analysis is usually too difficult. All right, that's it. Thanks.